Good evening, everyone. Welcome to today's leadership lecture series. So before we begin the lecture, I would like to take some time to tell something about the speaker for today. Mr. K. Ananth Krishnan is an MTech in Computer Science and an MSc in Physics from the Indian Institute of Technology, Delhi. He also has a bachelor's degree in Physics from Fergusson College, Pune. He joined TCS in February 1988 straight from campus. Mr. Ananth is currently the CTO of TCS and chairs the TCS Corporate Technology Board. He is a member of the TCS corporate think tank since 1999 and has led several strategic initiatives. He has been a principal architect and lead consultant in the architecture and technology consulting practice, and earlier the head of the TCS Systems Management and Systems Software Group. He was named in Computer World's Premier 100 IT Leaders for 2007 and in InfoWorld's Top 25 CTOs in the same year. He was named a Distinguished Alumnus of the IIT Delhi in 2009. He was also an invitee to the Quarterly Management Review with the TCS Board, the Executive Committee of Tata Sons Limited, from April 2000 to March 2004. He has served on several advisory boards of software companies as well as industry and academic bodies and government committees. He has served on the organizing committees of several national and international conferences. He is a senior member of the IEEE and of the Computer Society of India, as well as a member of the Association of Computing Machinery, and serves on the ACM India Council. He has been an invited faculty in the Department of Management Studies here at IIT Madras. He has formally retired from a successful career in trivia and quizzing, which includes the Brain of IIT individual title and 2 Cranium Cup titles at IIT and several years on the IIT quiz team, as well as public speaking, crossword puzzle solving, and cricket. I invite you, sir, please to come to the dais and share your knowledge with us.
Thank you, and very happy to be here. What I thought will be appropriate to this audience is to share my thoughts on where computing is at from a technology perspective and from the perspective of users and behaviors and so on. So if I look at the digital era, which we are all supposedly living in, let's first dive down into that and see what is the impact of the digital era on computing, on research, on innovation, and what is it that the market expects from all this good stuff that we are inventing. I'm going to take a bit of a negative example on over-promising and under-delivering on what the art of the possible is from a technology perspective. And then I'll talk about a few examples of actual intersection of computing and sciences, and I've tried to take a diverse set of examples from different sciences to show you what is the art of the possible is as we go forward. And then hopefully we'll have some time for questions. Okay, so what is the big deal, which is both an opportunity as well as something which is unfamiliar to some of us who are not really in the mental frame of mind. A lot of interesting work today, while it continues to happen in each of these 5 boxes that you see. I've drawn 4 boxes as horizontal boxes and 1 box, the computing box, as a vertical box, which kind of spans across all the horizontals. The interesting thing is that in material science, metallurgy, and so on, there are lots of exciting new challenges, whether it's discovering new ways of describing materials, new density function theory descriptions of a metal, molecular modeling of complex composites, and so on, and that's great. Right? Similarly, in the life sciences area, people are getting very excited about genomics and metagenomics and personalized medicine, systems biology, and so on, mathematics, and so on. So each of these is a very fertile area in itself. And if I look at computing, Computer sciences departments everywhere across academia and in industrial research are looking at algorithms and models and systems and so on, and there are specializations in each of these. So each science is doing fine from an opportunity to do new things perspective. But what is interesting is that if I take the intersections of material science with computing, if I take the intersection of life sciences and computing, and mathematical and statistical sciences with computing, social and business sciences with computing, those examples, bubbles that you see, they are even more rocket charged than anything which is individually happening inside a particular discipline. Yesterday I was in Pune at the National Metallurgist Day, and they had invited me to keynote on that intersection of material science and computer science. I'm least qualified as a metallurgist. I mean, I did do a master's degree in physics, as you might have heard in the very flattering bio that was read out to introduce me. Well, that's the closest I've got to metallurgy, in the sense that, yeah, I know the physics of metals, and I kind of thought I knew some solid state physics and so on, but by no means am I a material scientist or anywhere close to metallurgist. But that acronym that you see there, ICME, is what got me the ticket to be a keynote speaker at a metallurgist conference. Any of you know what ICME is? Have you heard about it? Okay, so you obviously know, I mean, you're right there. But clearly, it's something which happened. I think the acronym goes back about 8 years or so. In fact, we had as my co-keynote speaker yesterday a gentleman from the US National Academy of Engineering Committee, which actually coined that term, Professor Richard Lissar from Iowa State. And he was actually, after I spoke, then he actually did the right thing by saying this is the actual story of ICME. It's integrated computational materials engineering. So what does it mean? Materials engineers have used computation for many years. There's actually a sort of a discipline called computational material science, which is about using computers to solve complex models related to engineering of any material, especially metals. It's about numerical methods, it's about modeling, it's about simulation, it's about doing some kind of prediction on of the material properties by using closed form models. Okay, so that's been around for a while, maybe 30 or 40 years, because the mathematics for it has existed for many years. Okay. What has happened since this 2006 National Academy of Engineering report in the US is that there is actually a possibility to do much more with the availability of relatively inexpensive computing capacity, with the availability to process much larger amounts of data, and the ability to run new classes of algorithms against material science problems which are inherently very hard to solve in a closed form. So you can now use all the magic words which we in computing would be familiar with, which is like big data and which is like prescriptive analytics and so on, and you can solve problems at least in a reasonably timely way and reasonably inexpensive way to solve problems in material science which you would have not been able to solve otherwise. So it's not just that, because it is now the computational material scientists would say, oh, we have been doing this kind of approximations for quite a while, but if you now expand that ICME methodology to the entire materials life cycle, the materials life cycle is not just modeling and simulation. The materials life cycle is about saying, all right, for this set of properties at this scale, can I predict what would be the capabilities in terms of, I don't know, the weight of the material, the tensile strength, the fracture characteristics and so on, but can I now actually assert that it will meet the needs of this aeroplane that's going to fly 10 years from now? And these are the production characteristics of that material, which I've done it in a workbench in the lab, but once I take it to the manufacturing plant, I'll have to now actually do it in a plant scale. Once I do it in a plant scale, I have to worry about who's going to supply me all the different components, how will they fit together in the final product, how will they meet the actual requirements of testing and validation and destructive testing and so on in my finished product. The ability to do the models all the way from the atomic scale to the finished product, which might be a plane, a ship, a building, whatever, that is the integrated part of ICME. So when material scientists and computer scientists probably got together in the early 2000s to write this concept up, it happened in the US, it happened in Germany, and it happened in India 3 or 4 years ago as well. Lots of education institutions, research institutions, companies like TCS have now made this reasonably well known in terms of several workshops and actual products being built. The promise of this is pretty huge, which is great, because now you have a completely new area which can transform the way in which products are conceptualized to the way products are made, the way products are used, in a science which was probably not so good at leveraging the power of information technology. So that's one example of how science, deep science in one area, can now, by just intersecting with another science, come up with something very, very interesting. I'll pick one more example in the computational biology space. Any computational biologists in the room? Okay, so I can really tell you some stuff which neither I nor you know anything about, right? Okay, so what is the interesting thing which is going on here? The human genome was sequenced in its entirety about 15 years ago. Right? Craig Venter and his team were one of the first people, after spending $50 million and about 10 years of effort, they published the first sequence of base pairs, as they are called, ATCG, for pretty much all the 46 human chromosomes, and they said this is the human genome. Okay. There wasn't much that you could do with the full reading or readout of the human genome, but they did it. They were able to characterize every single base pair that goes into us as human beings. Since the year 2000, when this was first published, I believe something like about 500,000 full readouts of human genomes have been done. About 500,000 people have been sequenced. It's a fairly complex process, fairly expensive. The costs are coming down. You can now sequence a human genome for of the order of $1,000. It takes about a week to do a first pass of reading out what is it that goes into your ATCG sequence for the millions of base pairs or billions of base pairs that make it up. It's about a gigabyte of data. If you're a computer scientist, I mean, it's about a gigabyte of data per human genome. The interesting thing in genomics today is not just the fact that we can computationally process this amount of data, and we're getting better at it, both on the electronics side and the sequencing machines and the technologies to do it, and on the computer science side to be able to interpret the genome and to really start correlating it against interesting things. The interesting factor in genomics now is that, again, the vastness of data that is coming out of such studies is processable, just like in the material science context. It is processable, first of all, which itself is a big deal, because we couldn't process a gigabyte worth of data in anything less than a month 15 years ago. Today we can process it in a day, maybe 2 days. Secondly, we are now able to do something even more ambitious, which is to do what is called phenotype-genotype correlations at a scale which is unimaginable. What is this magic thing called genotype-phenotype correlation? I had no idea what this meant until Stephen Brenner, who is a professor at UC Berkeley and one of our collaborators in TCS research, Stephen explained it to me in a very simple way. He said, two human twins, identical twins, are about as close in genomic makeup as two human beings can be. I mean, it's 99.999. They differ in very, very few aspects from a genetic perspective. But they do differ, but it's a very small deviation. So their genotypes are almost identical. Let's take it as a first order approximation that their genotypes are equal. Great. So the genotypes are equal, which means their propensity to disease, all their genetic makeup is more or less the same. So if one has a gene which says you will develop, let's say, diabetes at the age of 40, the other person is also likely to have exactly the same gene. If it says that you're going to have dark hair, it's quite likely the other person will also have the dark hair gene, or in my case, the no hair gene. Okay, right. So you're with me so far. Right? So the genotypes are identical, so their external characteristics, etc., are likely to be the same. So Stephen explained it to me by saying, since the genotypes are identical and these guys are born on the same day, logically they should die on exactly the same day for exactly the same causes, assuming there are no accidents and so on, right? Have you heard of that ever? Twins being born on the same day, I think within, date boundary issues, I think by and large we all know that twins are born within a few minutes of each other. But twins dying on the same day for the same cause is unimaginable. In fact, we'd be very surprised if that is the case. So that is where phenotype comes in. Because our health, our lives, our characteristics, our personalities, in fact, everything about us is determined as much by our genotype as it is determined by our phenotype, which is the environment around which we live. So one twin might be fond of alcohol, might not exercise, might be eating all kinds of food, might be working in a certain, maybe in a mine or in a highly allergen prone environment, might develop a certain type of propensity for disease. In spite of his genetic composition, might ultimately develop or not develop any kind of health condition and live or die according to those phenotypic triggers rather than the genotypic triggers. So this has bothered geneticists ever since 2000 to say that, okay, we can sequence the genome, we can actually figure out all kinds of things about the individual based on the genotype, and statistically at least assert that yes you will or yes you will not have these kind of issues with your health makeup. But we also have to do a lot of phenotypic studies to figure out whether this will actually happen or not. And guess what? Phenotypic studies mean even more data and even more correlations to be done now with billions of variations on the genotype side and probably trillions of variations on the phenotype side. So if you're a computer scientist and somebody comes to you and says, you know what, I have this problem to solve, you would say, great, I can do this. So that intersection is now where things are really buzzing in every sense of the word. So there are as many computational biologists as there are probably traditional biologists in genetics today. And I'm sure in every academic department there is a fair amount of interest in just the sheer computer science challenges of handling this kind of a challenging problem set. I could go on about the others, but the point is that computing meeting sciences is probably being rediscovered over the last decade or so in academia, in industrial research, and in companies all over the world. So just bear that in mind as we think about what kind of impact the digital world will have on us as we go forward. What about the industrial world? In the past, the industrial world was relatively straightforward. The colored bubbles that you see on the top and the bottom of the chart is the way in which people thought about doing new things in specific industries. If I was in healthcare, I would have an agenda which says I need to worry about A, B, C, D, E trends in my industry. If I was in energy and transportation, I would worry about fuel efficiency, I would worry about energy production, I would worry about transportation densities and so on. And if I'm able to solve those opportunities and challenges, I'm good and I can be successful in my business. And so on, telecom and media and all the other industries. What has happened in the last, I guess, 5 years is that set of buzzwords in the middle that you see, they are no longer very conveniently packaged into one or the other industry. Why is that? The reason is that there is a fundamental shift which is happening because of the proliferation of digital technologies in every industry, which is changing the consumer. Now, for a moment, just think about each of us in the room as consumers of digital technology in some shape or form. our behavior, our connections, our ability to share data, our ability to access data, our ability to process information, every year is getting to be at least an order of magnitude better than the previous year. Right? I mean, since I am here in IIT Madras and you heard about the fact that I did a lot of stuff at IIT Delhi, the one thing which really stays in my mind is that in our hostel, as you used to walk in, on the right side there was a large desk which looked like the reception desk of a hotel, but for whatever reason there was nobody ever who used to sit there. But that tabletop used to be used by the postman to dump all the letters when for all of us who lived in the hostel. So when we came in for lunch, or whenever we were there in the lobby, we would look for letters on the table. And this was in the 80s. I don't think that desk is ever used for that purpose today. First of all, none of us write letters. And secondly, the means of a student staying in touch with friends and family has dramatically changed. There was one paid phone. You put in, I think, a 25 paisa coin in those days to make a call, a local call, because there was no way in which you could call anybody else. Outside the city and so on was just ruled out. But you could take calls in. So you used to write a letter to your parents saying, I will be hanging around near the payphone at 8 p.m. on Saturday, can you call? And they would call that number, and people would yell out and say, oh, your call for you, and we'd be happy to talk to your parents or whatever for some time, right? Now, given that was the case 35 years ago, and today in sheer information technology terms, with email, with Facebook, with Twitter, with cell phones, with all kinds of ways of staying in touch, the whole process of communication has been reimagined in that sense. Now, if that can happen in such a very important but relatively small part of our lives, think about all these other things that you see in the middle, which are things that people like me, heads of technology and research in companies, all worry about. All of these are super transformational technologies. These might redefine our industries in ways that even we struggle to conceptualize today when we have started working on them from a innovation and research perspective. And that is the promise, first of all, of each of those bubbles in the middle. The second concept that I'd like you to leave with is, just like intersections in the research agenda that I showed you in the previous chart, each of these bubbles in the middle, if you connect them with multiple industries, their effect becomes even more interesting. Let me take one of them, connected car. Right. Now, this is a project that you will see every automotive company is embarking on. Automotive or mechanical engineers in the room? Right. So, you might be familiar with this if you go visit a Hyundai or a Ford or a BMW or a Tata Motors or a Maruti or Mercedes Benz, whoever, they are all working on connected car. What is connected car? Connected car basically means that I can have the ability for the car to be in touch with the outside world using maybe the Internet of Things, which is one of the other bubbles on this chart, all the time. So, whether you like it or not, the car is talking to the manufacturer and sending data about the health of the car, the components, the fatigue statistics, the fuel consumption statistics, the tire pressure, the oil pressure, and all kinds of things. And the manufacturer would then proactively maybe even send signals back to set things right, or to warn you to come in for a checkup or replace something, and so on and so forth. The connected car also includes now internet connectivity for the driver and the passengers of the car. So, you could sit in the car and access your email, download a movie, and so on. So, that is the consumer experience side of a connected car. So, this is the way in which a automotive manufacturer would think about the connected car as a competitive advantage to help the automotive manufacturers sell more cars and be more successful as a car manufacturer. And all of us who are interested in the automotive industry would pour a lot of energy into it. I visited Waterloo in Canada a few weeks ago, and they showed me their connected car project. Right? So it was an interdisciplinary thing. There was a mechanical engineering component, there was an electrical electronics engineering, instrumentation people, computer science people, and they had stripped down one of the large SUVs, the North American cars, and they had packed it with all kinds of electronics, and it could sing, dance, and talk to the entire world all the time. Okay, fantastic thing, and it was a very good thing that 20 students and 5 faculty members had worked passionately to make this connected car happen. So absolutely great innovation opportunity from a automotive engineering, mechanical engineering, electrical engineering sciences perspective. Now, when people in telecoms and media heard about the connected car, they got very excited. Why? Because now they said, hey, listen, you can actually pump content into a car. I said, yeah, we can. They said, why don't we now have ways by which, if you are a subscriber of, let us say, Tata Sky, can you carry your subscription inside the car? You're going on a long trip and you want to, I don't know, watch the match, or you want to see a movie or do whatever. Do you have enough bandwidth for me to pump a Tata Sky movie into your car? Well, as long as you're not driving the car, I guess it's okay. So the automotive guy said, yeah, sure we can. So now there is a different model. So the automotive guy woke up and said, listen, if you're going to show movies inside my car, I work out all the safety issues and so on, what is in it for me? So now the telecoms guy and the automotive manufacturing guy are now potentially thinking about sharing the cost of putting in that movie system or the satellite TV system inside the car. So now there is a completely new business model being developed, that the car is not just something to get you from A to B, it's also a way to take your living room while you're going from A to B. And now you can watch whatever it is that you watch in your living room TV, you can watch it on as you're going. Then the insurance guys got interested. The insurance guys said, listen, you have the ability through telematics to tell me exactly what is going on in each component of the car. Wear and tear, maintenance histories, how many miles before the fuel gauge goes empty. Maybe you can even give me some safety statistics that I want on driver behavior. Is this guy driving too fast at all the times, or is he braking too hard, or is his ability to cut across lanes, something which is a highly risky behavior? Can you give me all that? So the automotive guys thought about it, said, yeah, sure we can. We have sensors to do half of that, and then we'll put in more sensors and give you all the data. So now the insurance people said, I can now actually rate a driver. Rate a driver is the terminology that they use to write the actual premium that the driver has to pay for buying insurance by using not just guesswork, but actual data as the car is moving. So now if I'm a safe driver, the insurance company might reward me by saying, you know what, we've been observing your driving for the last 2 years, and you are a very conservative, nice driver, so you know what, we're going to give you 20% off your car insurance. And the reverse might also be true. Right? If I'm an unsafe driver, they might actually raise my premium, even if I've never had an accident. Because now they're actually pulling the data from the connected car and using it for insurance rating purposes. More importantly, the insurance company now jumped in and said, can I now be the person in the middle to prevent accidents? How will that happen? A lot of accidents happen because brakes fail, or there is some component failure that makes a car get into a bad situation and so on. And so if the connected car can pass this information back to the insurance company to say that, you know what, this car has already done 40,000 kilometers and the brakes are now just 0.5 millimeters of tolerance left. Unless we change the brake linings, this car is definitely going to get into an accident in the next 3 months. The insurance company might send you a nice SMS text saying, here is 25 rupees or 50 rupees or 100 rupees discount coupon, please go and get your brake shoes changed. And you as a consumer will feel, first of all, very surprised that why is the insurance company feeling so, caring about me? Why are they doing that? Because if you actually do change your brake shoes for the 100 rupees or whatever it might cost, you're saving the insurance company a claim of 5,000 rupees. Because if you don't change the brakes, you're going to go hit somebody, and the insurance company has to pay you 5,000 rupees to get your car fixed. So to avoid a 5,000 rupee expense, they're giving you a 100 rupee coupon. You're getting your brake shoes changed, and everybody is happy. You don't get into an accident, insurance company saves 5,000 rupees, the car company has sold a brake shoe that they would not have sold otherwise. So new business models like this at the intersection of multiple industries are coming up and changing the landscape of the way in which these inventions are being done. So now the cost of the connected car is being shared by the automotive manufacturer, the telecom media company, and the insurance company. And hopefully all three are now able to say that I'll be able to give you a much lower cost of ownership of the car, and therefore everybody is happy in the sense that these super duper technologies are getting to a point where they will actually get adopted in some sense. I could go on with examples about every one of those bubbles in this way. Individually, an industry would be very interested in a digital oil field. Right? And this is actually true. If this is not the right season to go to Calgary in Canada. It's extremely cold there. I believe it's already minus 10 degrees centigrade in the day, and God knows what it is in the night. But Calgary is huge and buzzing because of tar sands. It's one of the most difficult terrains on the planet to do anything, let alone dig for tar and refine it into petroleum. Therefore, people are looking at technologies like robotics, they're looking at remote controlled oil fields, they're looking at sensor data coming in from all over the place at high temperature, high pressure, and so on. So computer scientists are actually working with people in the oil and gas industry to say, how can I help you analyze data so that the amount of time that you actually have to spend in digging for tar is the least and most profitable to do. So all these are opportunities. Again, think about intersections, think about collisions of multiple things. You have to be expert in your own field, but the ability for you to connect the dots with other fields to say, if I do this, who else can benefit, is now the way in which most people are thinking about innovation in an industrial context. I use this framework to summarize on how should one look at the consequences of research programs. We talked about research, we talked about innovation, but if you want to be able to channelize the outcomes that you want to produce, you need a reference framework. This is the framework that I use. It's not necessarily the right one, but I thought it would be useful for me to share this. So you got to be able to ask the question for a potential innovation opportunity. Innovation is the conversion of an idea into an outcome. You ask the question, what outcome will this innovation drive? Chances are that the outcome will be one of these four boxes. There may be a good way for you to anchor yourself. Some innovations result in simplification of something which we already do. It could be the simplification of a mechanical process, it could be simplification of a set of tasks that we do, it could be simplification of a human interaction of some sort. And that's usually a very good thing to do, because that is what drives progress in most human activities. The second box is what I have called digital reimagination. And this is something which is still emerging, because the power of digital technologies in the human hands is still relatively recent. It's about 10 years old. What does this mean? This basically says that as the access to digital technologies and information technologies grows, there is a super exponential impact on human knowledge and capability. We are still at the low end of that exponential curve, where the exponential curve sort of is still very close to the x-axis. But if it is truly exponential, which we expect it to be, then the impact is likely to be huge. Let me explain with some numbers. If I take the worldwide population number of 7.1, 7.2 billion, as of I think December 2014 or January 2015, the number of active mobile phones in the world will exceed the human population. So, with exceptions, that would mean that most of us would have some digital device in our hands, in our pockets, if not all of us on the planet. So, that is the first data point. A sort of subscript of this, one of my good friends, Krish Ashok, pointed out to me that there are actually more cell phones in India than there are toothbrushes. There are 900 million cell phones in India, and apparently only 200 million people buy toothbrushes in India. Right? So, a cell phone is more important in some ways than brushing your teeth. Okay? Whether that is true or not, we do not know, but that is an indication of the proliferation of the technology which has happened. Now, as the number of active nodes in this communication network increase, you know the power law kicks in, and the number of edges between people theoretically jumps up at a power law rate. Now, in theory that is bound to happen. In practice it is happening as we speak. The impact of that is what digital reimagination is about. What does a person do in any industry when you realize that your end consumer is a digital person? That is still being discovered by almost every industry. That is what, when we talked about connected car in the last slide, that is what is driving the connected car. That the digital technologies exist, and therefore what is it that should be done to really improve the capability of a person driving a car is what we are talking about. The third theme is governance. And governance has an impact or an implication on security, on privacy, on rules, on regulations, on laws, on compliance, all kinds of activities related to managing our day-to-day lives is the third innovation opportunity. Why is that important? Because of the sheer flow of information now, the ability for us to secure that information flow on one level, and also talk about the privacy implications of the vastness of this information flow. Both of these are challenges which did not exist before we started the digital technologies. Try this out. In fact, this is something which all of us should try to figure out. Try changing your privacy settings on any social network that you use. Whether it's Facebook, whether it's Google, whether it is LinkedIn, whatever is your preferred social network. Try going and changing the privacy settings to say, I don't want any of my personal information to be shared with anybody else. All credit to those companies. They've made it extremely difficult to turn it off. You can't do it. You'll have to spend almost half an hour to see which setting and which parameter you need to change to turn things off, and you have to do it in multiple places. But by default, a lot of the social network platforms that we use are making this data available to everyone. Have you noticed Google Maps recently? It has started having traffic flow patterns. I use it reasonably often because I drive to Siruseri every day, and I try to check what the traffic looks like. I now know it by heart, but just hoping against hope, I look at the map anyway. And it shows some red signs of traffic congestion everywhere. Any idea how they do it? Does Google have satellites which kind of look at the traffic in OMR every day? They don't. They bought a company called Waze about a year and a half ago, Israeli startup company. What does Waze do? Waze basically buys cell phone location information from the telephone companies. So far so good. What Waze does is it overlays that information on Google Maps. And so if there are 500 cell phones which kind of are on the OMR, It's unlikely that 500 people are taking a stroll on OMR at 8 o'clock in the morning. They're probably in buses and cars and so on. So they just translate that phone density on a road to traffic. Reasonably good assumption, very useful, almost always accurate. Good so far. Now the poor fellows like you and me who are on that road, it's our phones which are telling Waze and then Google that there is traffic on the road. Now you can turn it off if you want, but very difficult to do so. Because your cell phone company is selling the data on an aggregate. They're not selling your phone data, they're just selling 5 million phones data to Google. Privacy issues like this are huge. And there are many, many such examples which will come up. The last innovation category is sustainability. Because all of these are the upside issues, opportunities, sell more, simplify, digitally reimagine and so on. But we have to worry about the sustainability of all the things that we do. Whether it is health, whether it's ecology, whether it's power, energy, education, all of that which are societal concerns are also big drivers of innovation. So I use this framework to sort of mentally calibrate what the scope of the things that we should be worried about. On one level, it's very easy to be carried away by the technology and the science, but on the other side, this is a good balancer to see this is what we should worry about. Talking of balance, I thought this would be an interesting case. Many of you would have heard about this interesting example that Google is known for, in the sense that by just analyzing search terms, Google was able to, in many ways, not just predict but accurately model disease conditions like influenza. This one is the flu trends report. Right? So by just checking on which cities or which towns are people searching for terms like flu and cold and fever, they were able to say that there is a flu outbreak in this particular town. And this was cited by so many people, and it became a poster child for the power of the so-called big data world. More recent research shows that there is actually a problem with this, in the sense that while there is some arguable correlation, it is not as perfect as it was thought to be. This is the kind of peril that we have to worry about when we start looking at data as a driver of science. There is always a scientific method which hopefully all of us adhere to, which is to say that I make a set of observations and I create a hypothesis and I try to describe it in some form, hopefully mathematical, and then I verify that against my observations and see whether I can then make some predictions, and then you are able to say that yes, this model is sound. It goes back to the Greeks, it goes back to the ancient Indian philosophers, it goes back to Newton and Galileo and everybody else, right? Whereas this kind of thing is that I have a mass of data, I just fit some models against it, and if it looks kind of half promising, I go out and publish it, and then wait for somebody to shoot it down, right? So it is a very inverse model way of working science. Sometimes it works. A lot of genomics and genetics, by the way, is like this. Right? There are lots of companies today which will say that I can do a genomic sample and run predictions against 60 diseases or 80 diseases or your ancestry and so on based on your genotype. For like $50, $100, you can take a sample of your cheeks, inner cheek lining, send it to them in a kit, and they will run that report for you. Bear in mind that that is all statistical inferencing like this. Right? It need not be very accurate. So if they say that your ancestors were from, I don't know, Greece or Turkey or whatever, yeah, they probably were, but don't swear by it. That's the basic thing. There's a lot of noise in these kind of big data analytics that you have to worry about. I'll close with a couple of examples in terms of how to apply this in the social sciences. This one is about this very tough thing called human capital valuation. And since universities and education institutions, research institutions are pretty much in the process of building up human capital, This piece of research is from our innovation lab in Pune, and this basically is trying to model the human capital valuation of TCS as a whole and potentially human capital indicators for an individual along these 7 different dimensions, whether it is technical knowledge, whether it's innovation capacity, whether it's communication, diversity of experience, and so on. We use proxies, trackers as they are called, estimate those by taking it through the HCV estimation engine, and then run all kinds of analytics against those dimensions to, first of all, assert a certain human capital value, and then to scientifically project it, and then to track it, and then hopefully help the individual to develop further. The developmental psychologists and the HR professionals in TCS are super excited with this. And we are actually now rolling this out in some small experiments and so on, and actually testing it with live human beings. This kind of capability set was unimaginable 5 years ago because the vastness of variation of data was a killer. But today, the computer science is good enough to do this. I'm still not sure whether the human and cognitive sciences are able to figure out whether this is right or wrong. So this is work in progress. If any of you are interested, we can connect you with that team, and then we'll see how we can actually improve this as we go forward. This one is another aspect of computing and social sciences, which is about human connections. This is actually a snapshot of our internal social network. It's called NOMI. Think of it as an internal Facebook which runs inside TCS. Those red blobs that you see, the green blobs that you see are units or shall we say business parts. They could be, in your context, they could be departments or hostels or whatever might be an aggregate that you use inside the institute, and the influence that they are having on their next nearest neighbors, right, or the larger organization. So if you're a red blob, then you are a very tightly integrated influencer of everybody around you. If you are a green blob, then you're influencing only your community, but you're large in that sense. The blue blobs are sort of intermediate, and they are basically saying that these are communities which are very insular, but they should be strong influence. So the corporate HR department, for example, should be very tightly connected with the rest of the company. They are therefore inside the core of the company, but they are not going up the scale. They are not yet a red blob in that sense. We are now able to do a tremendous amount of analytics on what we call the social influencer behavior of individuals within the company, groups within the company, communities within the company, and so on. And we don't know where the science is going to lead, because now we have started hiring a lot of social scientists to help us interpret this data, but the data is there. And we are now able to see and predict and even model certain types of things in a way that we were not able to do as we go forward. This one is about data being produced by data centers, networks, physical equipment, routers, switches, servers, storage elements, and so on. They also produce data. So we are doing deep analytics on each of these and trying to now predict the way in which an IT plant, which is a data center, is going to behave in a way going forward. So the common theme across each of these is 3 completely different areas. One to do with human capital, one to do with social capital, the third to do with machines inside the company, are all throwing up opportunities for potentially doing very interesting things on the digital dimension with each of these. So let me summarize what I've been talking about. Computing today is not just an interesting science by itself, but it is becoming even richer when it intersects with other sciences. I talked about material science, I talked about life sciences, social sciences. Each of these is yielding completely disruptive new ideas from a pure research perspective. And the lesson to be extracted is that expertise in your core area is important, but the ability for you to connect with experts in other areas is equally important. And together, much larger problems can be solved. From an innovation perspective, from an industry perspective, the same thing seems to be holding true. It's not just an industry trying to be competitive in itself, but an industry trying to look at the adjacencies of the industry and saying that what if I do this, who else will be interested? We talked about the connected car and a couple of other examples. Those are precursors of the way in which many of these new technologies will take shape in the real world. And that is only bounded by the imagination and the business potential of each of those innovations that we are talking about. The caution that we applied was that we need to be careful about the way in which we use this capability, the digital capability, before we jump into sort of nearly infallible conclusions. We have to apply scientific rigor and make sure that those are actually valid conclusions and do it in a way which is trustworthy. And lastly, we looked at a few examples of the potential of these technologies in communities and individuals, in learning, human capital, and even data centers and physical equipment maintenance as we go forward, that these all could be fresh new areas for reimagining ourselves. With that, let me stop, and if there are any questions, I'll be happy to answer. So I don't think it's a showstopper in today's context, in the sense that voice communication with a handheld device is nice to have, it's useful in emergencies, but not everything in life is an emergency. Right? So if you structure yourself reasonably, you can get away with it. I've never carried a cell phone. So. Right? Great question, and it's I don't think there is a perfect answer to it, but what I do, because I head research for TCS in addition to technology and innovation, the question that I ask the TCS scientists is twofold. One is it worth doing from, or a research idea, is it worthwhile from a pure creation of knowledge perspective? So first of all, that the quality of the idea that you're researching should be good in itself, intrinsically good, which can be only judged by, let me call it the research merits of the idea. So it should be publishable in a good journal or in a good conference. It should be passing through rigorous peer review to make sure it is truly original and new and so on and so forth. So that's the first prerequisite for any idea. Right? You might file a patent on it and so on. So all those are indicators of the quality of the idea itself. So that's the prerequisite. So therefore, should I even think about the commercial potential? I would think about it only if it has crossed this basic criterion, that the idea should be good and recognized to be good. Once it is published, it is patented, accepted in a conference, whatever might be the method, then you start looking at it from the perspective of what can I do with it. So that is where it crosses from the research or the invention side to the innovation side. Now, how does one judge the potential of that? You ask the question on whose problem is this invention going to solve? It's a very good way of thinking about it, not so much from the idea to the outcome, but ask it outward in to say there is a potential set of human beings, machines, whatever out there on the planet. If I do this, whatever this idea is, whose life is it going to change? Right? So you ask that question outward in. If the answer is that yes, it is going to fundamentally change something in somebody's life, the second question that you ask is, how valuable is that change to that individual? Is that change something which they would just say, okay, nice to have, but I can live without it? Fine, you might still do it because it's good to do, but it may not be very highly commercial in its value. But if it is fundamentally changing somebody's life and that change is valuable to that individual's life, then you're on to a good thing. Right? So if I look at some recent examples, you know Uber, the taxi service. Have any of you used Uber? They are there in Chennai. Do you know how Uber works? Uber basically solves the problem of calling a taxi and using a taxi. All of us or many of us would have used a taxi service, call taxis. What is the process? You call the call taxi, now some of them are smart enough to say, okay, based on your mobile number or the phone, they would pretty much know your address and so on. Then they would say, yeah, a taxi will come in half an hour, then it doesn't come in half an hour, things go back and forth, then you take the taxi, the guy goes there and there's a meter and then you pay cash and he says, I don't take credit cards. Reasonably good process compared to our good old autos, right? Now what does Uber do? Uber basically asks you to pre-register. So you register with your name, your address and your credit card. Okay. So once you're pre-registered, you basically tell Uber in some way, either by calling them or SMSing them or from the website, say that I need a taxi and I need to go X, whatever is your destination. Uber will send you back a communication, which could be an SMS text, it could be an email, it could be a call center voice call, whatever, to say a taxi will be with you in X minutes. So far so good, almost identical to your call taxi booking service. Now Uber is able to give you real-time tracking of your taxi. If you have a cell phone, it works best with a cell phone application or a tablet application. You will know where is your taxi which has been assigned to you, where is it. You get picked up, you get dropped and you just go. There is no payment. Why? Because the moment the person drops you, the start and the end points are known, there is a fixed fee and it gets debited to your credit card. So you basically just walk off the taxi and you're done. Right? So booking is easier, tracking is easier, payment is easier. It is revolutionizing taxi services all over the world. Business model wise, it is very, very disruptive as well, because you or I could be a Uber taxi driver. And that is where the legal situations are coming in. So now the fundamental point that I am trying to make is that the people who thought about Uber thought about not the technologies, which is GPS tracking and mobile payments and a few other things that go into the technology, but they created a business model to fulfill a customer need. Customer need was that it is a painful process to get a taxi in most countries of the world. So they solved the painfulness of the process with dramatic ease of use, and they are now at least a well-known name. I can't say they are very successful yet. In many countries they are, in other countries they are not, but they have revolutionized the simple task of calling a taxi. So that's a very trivial example of an idea, because it changed somebody's fundamentally their life in calling a taxi, which is a very small piece of our lives. They are become fairly well known. So any idea like that, if you go outside in, it might give you a better handle on what the commercial potential is.
So after that, do you stack it up or do you declare it obsolete?
The data itself?
Data itself.
Mm-hmm.
And if you are declaring it as obsolete, how do you do that?
So it depends on the discipline or the area in which you are doing the data analytics. In most cases, the data will persist beyond your first use. Take the originator of the word big data, which is Google. Right? Google basically mines a tremendous amount of information from the web through the famous PageRank algorithm. It mines a lot of information from search. Each of our search queries gets analyzed in itself. Where is the search coming from? Who's searching it? Which location? Which time? Which country? And so on. And thirdly, they mine all other kind of data sources, including Gmail and Google circles and so on, which basically give them behavior information. Once Google does a particular type of analytics on that data set, they don't throw away the data. They keep the data, they repurpose it, and they might run another set of queries against the same data, and they might get a totally different insight based on what the question is. So by and large, data would outlive the first use. There may be exceptions where the data is very time sensitive, in the sense that it is relevant for a period of time. So a stock market pricing data set would be interesting to store for future use for doing some kind of a back analysis of why did this stock price go up this way 2 years ago on this date and so on. So somebody wants to do that, yes, you need to persist the data. But most stock trading algorithms, the so-called algorithmic trading things that a lot of the analyst firms do, they throw away the data the moment they have placed the trade, and that instant is literally in microseconds, because they have to now move on and make the next recommendation for the next buy or the next sell, because that's how fast the data moves. So in that case, yes, the data on which they operated is thrown away and then it's refreshed, but they still sometimes archive it so that for forensic purposes later they can still analyze it and see what happened. So in general, 9 out of 10 times, 99 out of 100 times, you would persist the data beyond the first use. Some time sensitive ones like trading, you might have to throw it out. But since storage costs are cheap, you pretty much end up with all kinds of data. In fact, one of the big problems or the opportunity, if you will, for the life sciences people I talked about, the genomics people, is this rationalization of data sets. Large data sets which are there in genomic analysis, they are truly large. As I said, a typical human genome runs into several gigabytes. And they keep, let's say there are 10 students in a lab and they keep running these analytics and so on. They keep persisting the data, they never throw it away. And it has to be stored, it has to be managed, because in most countries, genomic data is sensitive personal data. In India, for example, you cannot send Indian genomic data out of India. The law says so. So if you're running a lab here, I'm sure there is a genomics lab here, right? There's a structural biology department here. And if your students there, you better pay attention to the data, because under the law, if you lose the data and somebody puts it in their pocket and walks out and takes a flight to the US, technically you're breaking the law. Right? So the data is persisted. You should then wipe the data after you have used it. Most people don't. It just lies there, because it's the data storage is so inexpensive. For 1,000 rupees, you can buy a terabyte of portable storage. Thank you.
Thank you, sir, for such an insightful lecture. May I now request Dean IR, Professor Nagarajan, sir, to present Mr. Ananth Krishnan with a memento.